In this lecture, we're going to discuss helical coil compression springs loaded with static loads. And before we start talking about how to solve the problem, let's first remind ourselves what a helical compression spring is. A helical compression spring is primarily designed to resist compression. So in other words, when you push on it, it pushes back. So the question is, how are forces generated within the spring that allows it to push back? In other words, when a force is applied at the top of the spring, what happens if we do a cutout and take a look at the individual portion of a coil to see what's going on force-wise to generate or to transmit those forces down to the base at where the supporting load is? And the answer is, what's happening on the inside is actually a torsion load. Now you can see this if you were to take a coil spring and put it in your palm and begin pushing down with your other hand, you'll find that the bottom of the coil spring wants to turn. Matter of fact, you'll kind of feel it dig into your hand as you begin to push at the top. Or if you want to put it on a piece of paper and begin pushing at the top, you'll notice that the coil spring at the bottom wants to turn into the page. And the reason that's happening is that there's a torsion that's created inside of the coil on its way down. So the aspects of the spring that we need to consider are first the wire diameter. We talked in the last lecture how the diameter of the wire affects the strength of the material, and now we can see that what we're going to do is we're going to take the diameter of the wire and then wrap it, so that another dimension is the coil diameter. And what we're talking about the coil diameter is the mean diameter of the wrap. In other words, from the center of the small diameter to the center of the small diameter of the other side. That is what we mean by the mean diameter. Of course, that means that the outside diameter will be the mean diameter plus a wire diameter, and the inside diameter will be a mean diameter minus a coil diameter minus a wire diameter. This leads us to an important aspect of our spring design, and that is called the spring index. The spring index is a ratio of the coil diameter to the wire diameter. And in this class, we're going to say that the coil diameter needs to be between 4 and 12. As the coil diameter gets, or as the spring index gets small, as this number gets below 4, what we'll have is the wire diameter is very large compared to the coil diameter. And so the shaft that we're going to have to wrap around will not be any stronger than the wire itself. In other words, this is really hard to manufacture. It has a tendency to break the shaft if you have a spring index less than 4. As the spring index gets large, especially as it grows beyond 12, what we're going to see with the spring index over 12 is that it's so wide, it's kind of like a slinky. And if you've ever had a slinky for very long, you understand that if you put it in your box or wherever it's stored and come back to it later, it has a tendency to get tangled. And so springs don't transport well in groups unless the spring index is less than 12. So those are our two limiting factors for the spring index. So besides wire diameter and coil diameter, we also are going to have the total free length of the spring. The free length of the spring is nothing more than how long it is when it is absolutely uncompressed. And then we have the number of coils. So if we count the actual wraps, start on one side and start counting, so 1, 2, 3, etc. That's the number of total coils. And then the coil pitch is the distance between the two. And it should make sense to you that only 2 of these 3 are unique. In other words, if I have a free length and number of coils defined, then of course the coil pitch is defined by the other 2. So when we talk about designing a compression spring, this is what we mean. When you call up a manufacturing company and have them make it for you, you're going to be telling them what wire diameter you need, the coil diameter you desire, its free length, and number of coils, or at least 2 of those bottom 3. And I think the best way to illustrate how to solve a problem is actually to walk through the solution to the problem, and so I'm going to do that in just a minute. But just as a generic overreaching view, first thing, normally we're given forces and we're finding the geometry, or we're given geometry and finding a force or some sort of combination. So very often you're told we need to have something that responds with 10 pounds of force, and you can define the spring and how much compression it can have. Or maybe you're told the spring is going to compress 4 inches and you need to know how many pounds it's going to push, or something. More often than not, it's a combination of the two. So we've got room to put a 4-inch by 2-inch spring in here, and it needs to resist 10 pounds, something like that. Now, one of the nice things about spring design, especially in contrast to some of the other elements we looked at, when we looked at bearings, we said that bearings are typically designed very downstream of the rest of the design process. So normally, by the time you got to designing a bearing, you were pretty limited in the choices you can make. Springs are not that way. Typically, they're higher up in the design. And so that means, although it's very difficult to get an exact for what your initial problem asks for, you probably have some room to push back as a designer and say, well, I can't give you 10 pounds, I can give you 10.2 pounds. Is that sufficient? And work through it that way. So that means you typically are allowed to change other aspects of the design while you're designing the spring. One example of a flow would be to choose a guess. So by a guess, I mean a diameter of the wire and a diameter of the coil. From that, we're going to find the maximum shear stress within the spring. That's a function of the forces that are being applied and the diameters of the spring. If that's satisfactory, we'll find a factor of safety. Now notice, this is a factor of safety of yield strength divided by shear stress. Up until now, anytime we've seen a factor of safety, we've always done it as not shear strength, but tensile yield strength divided by tensile stress. And so we're shifting. Instead of using normal stress, now we're going to use shear stress. Instead of using tensile strength, now we're going to use shear strength. And that's because springs are seldom loaded as beams as well. They're almost entirely always just in shear. So it makes sense to look at factor of safety in terms of shear strengths and shear stresses. Now we'll iterate on this side until we're happy with our factor of safety. From there, the next thing we'll do is figure out, compare our desired spring constant, which is almost always something that's given to us. How much are we displacing and what forces do we want it to give us as we displace? And then we're going to find what our actual spring constant is. And this will tell us we're going to decide a number of active coils to figure out how this spring constant is actually made, and again we'll have to iterate from this point to make our actual close enough to the desired, and then finally we get a total length. And again, the aspects of this formula are the diameters, the type of material, and the number of active coils. And then here we have number of active coils, the spring constant. The spring constant that we're going to use here will of course be our actual spring constant. There's no reason to even talk about what we wish it would have been with the desired spring constant. Then our actual forces and the wire diameter. All right, so this gives us kind of a generic idea of how to solve or at least one possible design flow for static helical compressive springs. Let's take a look at a specific example. So suppose I have a helical compression spring. We've got a static load of 45 pounds and a deflection of that static load at 1.25 inches with a factor of safety of 2.5. We're going to be told at the beginning of this problem to go ahead and use a spring index of 7.5. Remember, it needed to be between 4 and 12, so that's satisfactory. And then we need to specify all parameters necessary so that we can actually produce this spring. So a couple things to note. First off, the deflection of 1.25 is what we're going to call our working deflection. And notice there's nothing here mentioned about what the initial deflection is. That's unusual. Normally springs have some sort of initial deflection. And this one we're not told anything about that, so we'll assume that our initial deflection is equal to 0. So translating what we've been given into given values, we know that the working load is 45 pounds. We know that the working deflection is 1.25 inches. We have a factor of safety of 2.5, a spring index of 7.5. Okay. As we work with spring problems, we're always going to use that the springs are made out of some sort of steel, and because of that, we're going to take 11.5 MPSI as our modulus of rigidity. Now be careful here, in the back of the book you might find steels that have a different modulus of elasticity, but this value I have listed here is the modulus of rigidity for the springs listed in the spring table that we alluded to earlier. And again, since it wasn't mentioned, the initial deflection here is equal to 0. Now, the first thing I'm going to do is I'm going to go ahead and make a decision about what to do for the ending of the springs. You notice here there are 4 different types of endings. The first one is just basic. What we're going to do is we're going to take our wire and we're going to wrap it around some sort of core. And as we wrap it, we'll get a length and then just cut it at the beginning and ship it out. That's it. So that's called plain ends. And the number of active coils is equal to the number of total coils. Matter of fact, what that means is that all of these coils and every section of the spring is helping to generate the spring force. Down here at the bottom, in case B, the number of active coils is equal to the total number of coils minus 1. What have we done? We've taken our plain ends and we've grounded it flat. And the reason we've done that is, if you can imagine, a plain end spring will not stand up very well on its own. So the ground end is going to allow it to have enough of a flat surface that maybe it will be able to stand flat. Okay, another way of doing that, instead of grinding it, would be to actually compress the first and last ends. So what we're doing is we're bringing this end down so it's actually touching the coil next to it. And by doing that, it actually costs us 2 total coils. So our total coils minus 2 is what our active coils are. The active coils are the ones that are actively helping us resist our motion. And then finally, the combination of the two, if you start with squared ends and then ground it flat, this will be squared and ground, and this one is the easiest one to stand, most balanced. Notice that squared end and ground ends both are total coils minus 2 is the number of active coils. So we need to make an assumption here about which one we want to do. Now, something else I want to talk about before we walk through the problem as a whole, what do we mean by the desired spring constant? Well, we've been told that our working force is one value and our working displacement is another value. So the two of them together will give us, let's see, it's 45 pounds for the working force and 1.25 inches for our working displacement plus our initial displacement of 0. That'll give us a total, our desired spring constant will be 36 pounds per inch. Now the formula for actual spring constant, notice the difference. This one is working with forces and displacements. This is what we desire out of the spring. This is working with the diameter of the wire, the diameter of the coils, the number of active coils, the modulus of rigidity. So this is a function of material. It's a function of number of coils and wire diameter and coil diameter. So this is what it will actually get when we assemble our spring. And the difference between the two halves of these equations, this one's written in terms of a spring index, which is pretty common as we design our springs, considering spring index as an assumption at the beginning. So what we'd like to do is we'd like to find a way to equate these two forces these two equations to each other. In other words, I want my actual to be equal to my desired spring constant. Working this equation around, this is going to give me that the number of active coils is equal to a function of everything else. And I'm doing that because that's really the only unknown here in the problem. I'm going to start with an assumption. We've been told 7.5 is what we're using for the spring index. We're going to decide a D, a diameter, and G comes, that's a given. So we know everything here except for the number of active coils, and that allows us to design for number of active coils as a function of diameter. Now again, I want to stop here and make an important note. When we manufacture real springs, in general, the equipment used to make the number of coils is going to cut off at the quarter coil. So when I get this number of active coils, I'm going to have to round to the nearest quarter coil. I'll talk more about that once we get our final answer as we work through this example. What I've done here is I've worked this equation down, so now it's a function of diameter. I know I'm going to need to make a guess for what this initial wire diameter should be, and so I'm putting the number of active coils as a function of that diameter. It's not necessary in a lot of problems, but this particular one, it'll work out nicely for us as we move through. All right, if you remember, the strength of the coil was also a function of the diameter. So what I'm going to do is I'm going to go ahead and make a selection of what type of material that we're going to use, and then once I do that, I can now have my ultimate strength also as a function of diameter. So this is going to again work nicely so that I can pick a diameter, solve for what the factor of safety ought to be, and check very quickly whether that's a suitable diameter or not. And table 14.8 in the book shows some really important statistics, but before I talk about what these statistics say, let me describe what setting a spring is. Now, this is one of those places where apparently the concept of setting a spring was done with people that didn't talk to each other much. So we actually have two different ways of saying the same thing, and it sounds like they're backwards. So I'm going to try saying it one way, and then I'll say it the other way. What we mean is we're going to take our spring and we're going to compress it so much that all of the coils are touching each other. Okay, this is called setting the spring. So by pushing the spring until it's collapsed, when you remove the stress that caused that, the spring will rebound but not to its original position. It will not be quite as high as it was originally. Again, that's called setting the spring, or another way you can say that is it's called removing the set. I know that sounds backwards, but that's just the two different ways that this is notated. So setting the spring and removing the set means the same thing, and it means that you compressed the spring until the coils were touching each other, and when you released it, it was not as tall as it was. Now, something interesting about that is setting the spring actually makes the spring stronger. So for instance, for our A227 and 228, the yield shear strength of a spring is going to be 45% of the ultimate tensile strength if I don't remove the set. But if I remove the set, then we'll be able to use, I'm going to use the bottom number, so 60%. So it means we gain a 15% strength if we're able to set the spring before we use it, or if we're able to remove the set before we use it. Okay, so again, what this table is going to give us is that we're either going to say that the yield strength is 45% of the ultimate tensile strength, and notice this is tensile strength and this is yield shear strength. So I'll show that equation as we work through the example. All right, so our total factor of safety is going to be equal to the yield shear strength divided by the stress, the maximum stress that's in the material. Now, we know that the yield shear strength is equal to 0.6 with the set removed. Again, backing up a slide, that's coming from this equation right here, 0.6. And this is A228, which is the material that we're using. Okay, so we've now chosen the A228 wire. We know that our ultimate strength, we're going to pull values for A and B. That again comes from these two tables. So A and B, the minus 0.1625 is what we're seeing here, minus 1.265. Now we're going to solve this equation for the shear stress, and this is going to tell us that the maximum shear stress we can have with a factor of safety of 2.5 is going to be, again, a function of D. Now, by maximum shear stress, what I'm interested in is when will this occur? At what period of time should this stress be the highest? And the answer is when I actually shut the spring. In other words, I'm not interested about before the spring starts. I'm talking about when we put the maximum load and maybe even beyond that load. If the spring closes all the way so that the spring is shut, are we going to still have a factor of safety of 2.5? And that's the stress that I'm interested in when the spring is actually shut. So let's talk about what's actually generating the shear stress within the spring. So what we're going to do is we're going to take a free body diagram and do an internal break here and take a look at what's happening at this location. And I'm going to kind of spare you the details of solving the free body diagram and just jump directly to it, that what's occurring at the wire, if we were to zoom into this one corner, we take a look, and what we would find is that there is an evenly distributed direct shear that's caused by this force that's happening right here. In other words, the spring is trying to be sheared in two. Okay, so that value is going to be our force that's being applied divided by the area that it's trying to shear. That's the wire diameter area. And that shear, that's one of the aspects of what's happening to our element that's undergoing stress. So if I take that area and again insert pi wire diameter squared over 4, I'll get a relationship now with respect to the wire diameter. Now the other aspect that's happening here, you can see there's two things going on. There's a force that caused the shear and there's the torque. is we have a torsional distribution. So what this means is that we need to analyze something that's happening out here on the point. Matter of fact, I'm looking at 2 points, and it's clearly that this is the one that's going to be the highest because this stress is going in the same direction as the stress above. So at this point, the stress caused by the direct shear and the stress caused by the torsional shear will align and be in the same direction. And this we've already discussed before. If we have something in torsion, it's TR over J. And again, plugging in for the wire diameter, we now have a function of wire diameter and the force. Notice this capital D, this D is the coil diameter, and that's coming because this torque is created because of a distance that it's offset around. If we sum those two together, we see that they superimpose on top of each other so that we can see that the maximum is the stuff that's caused directly by shear and the stuff that's caused by the torque. So these two together provide the maximum shear stress that's going on. If you recall, the spring index relates the coil diameter to the wire diameter. And now I'm going to introduce something that's not very apparent necessarily looking at this. And what I'm going to do is I'm going to notice that there's this d squared and the d cubed and the capital D. And so what I'm going to do is I'm going to introduce a constant. And don't worry right now about how I derive the constant, so much as to notice that by taking this constant and applying it, we can have a little bit of a simpler equation. What we've done is, if you notice that here's the 1, that's this portion right here, and the 0.5 over c will result in this portion over here. So this allows us to have a nice constant that's a function of the spring index being multiplied by other values that now very easily find for us what the maximum stress is. Now there's one more aspect that's a little bit more complicated, and that is the beam is that the coil of the spring as it wraps around is not a straight. Our assumptions were really that this coil is behaving not as a curve but as a linear beam. Since that's not the case, we need to add the effect of the curved beams. Now, I'm not teaching that in this class, but if you add that, what you'll find is that the curvature gives it a parabolic shape here. So this is effect, this curved, is the total superposition of all other factors, and this is also showing the effect that the spring is wound in a round orientation as opposed to a straight beam. And what we'll do is we'll introduce another kW, where kW is defined as 4c minus 1 over 4c minus 4 plus this ratio of 0.615 over c. And again, I'm not going to derive for you how we got to this Wall's constant. This is I'm just going to tell you that this is taking into effect the curvature of the beam. So we've got two constants here. Either we're going to use Ks or Kw. We need to talk about when to use which value. If the load is loaded statically, as we begin to push down, there will be local yielding. Again, we're using material that is ductile, and you're used to seeing the effect of stress concentrations go away as you use ductile material, and that'll be the case here. So if we're loaded statically, in this case our 45 pounds that we're pushing just one time, what we'll be able to do is use Ks. We won't have to take into account the wall constant or the curved constants. On the other hand, even if we load it dynamically, if we remove the set, we cause there to be a stress, a relief of the stress, and so we'll still be able to use Ks. So the only time we have to use Kw is if we're loading it dynamically and the set was not removed. That's the only time we need to use Kw. As we begin talking about shutting the spring, we need to talk about how displacements work and how they're listed. I'm going to try to be as consistent as I can here, and I'm going to follow the book's notation. The way the book notates things is, if we're talking about lengths, it's a capital L, and we begin measuring from, I guess you could call it the bottom of the spring. So we have our free length, and then we reduce it to our preload length, and then we reduce it more to our working length, and finally to our shut length. If you notice, the shut length is when the spring is actually touching, all the coils are actually touching each other. We are going to try never to design all the way to shut. The reason we're going to do that is because the spring dramatically changes how it behaves once all of the coils are actually touching each other. So we're going to have our working displacement, and then we're going to have this extra little bit that we're going to call Y clash, and that's going to be another kind of, you can kind of think about it as another safety net to make sure we never shut the spring entirely. The stress we were interested for the shut stress is actually going to occur if this were to happen. So we have another factor of safety kind of built into the spring in Y clash. Notice though that these Y values, so L is talking about lengths, Y is talking about displacement. And you should always be able to take at any particular state the length plus the displacement to get back to your free length with no load. So initial displacement, a working displacement, and then finally a clash displacement. What this means is that if I take a look at the total amount of displacement necessary to shut the spring, it will be equal to the initial displacement, the working displacement, and the clash displacement all added together. And very often the way we're going to define this is with an alpha, which is a percentage of the work. That's what we'll let our clash displacement be. All right, so going back to our stress at the shut, when the spring is shut, we now have tau shut is equal to F shut. We're going to take our spring constant, F shut divided by Y shut. Notice that this spring constant, K, is applied right here at the shut displacement, but we could have just as easily used F work divided by Y work. And that's actually true with all of these equations. If I'm looking at tau, the difference between tau shut and, for instance, tau initial is F shut versus F initial. So these are general equations that can be applied to any state as we move through the spring. Now what I'm going to do is begin substituting in. I'm going to solve this equation here for F shut and then apply it down here. So an F shut now becomes our spring constant times Y shut. And Y shut was defined as our working displacements, so the initial, the working, and whatever we decide for our clash displacement. And notice now I've also went ahead and applied the value for what I knew K was and plugged it into the equation. So now we can throw everything together. We have this equation here, which is again a little bit reworked, but that's the same equation I just showed you. The initial displacement was equal to 0. What I'm doing here, follow what's happening here, Y work is, again, we come back up here to this equation. If we take the K as a constant, if we take F work divided by K should be equal to Y work. That's this term here, F work divided by K. I still have my clash displacement. If you remember, our initial displacement was equal to 0, so we've applied that now. So we have that on one side. And on the other side, we found that we had this equation for the factor of safety, which we know, and another function of diameter, which is the ultimate tensile strength for our wire that we've chosen. And so plugging everything together and rearranging, we actually can solve this now directly and say that the diameter raised to the b plus 2 is equal to this massive equation. So now if we set what our percentage is we want, and F work we've been given, everything else we know here, the only thing we don't know is what we're going to set our clash displacement to be, and then we can back solve for what D should be. Now I showed you this almost in contrast to the example that I said at the beginning about how we would do this. I did this one analytically instead of by following a general design. And so another option, maybe the option you would prefer to use, would be to take a guess with diameter and get all the way to the end, and you're just checking to see whether or not the factor of safety is satisfactory, and if it's not, then you change a different diameter and move it around. So applying specific values, okay, plugging everything in, I'm going to take as a displacement of 15% of the working displacement for my clash allowance. This will give me a wire diameter of 0.13 inches. Now there's only one problem with doing this. The value that I actually solved, this 0.13, is not available. If you go back to the tables from the last lecture and we look for diameters, the closest diameter I can come to is this one right here. That's 1/8 of an inch. So this might not have even been the best method. Now that I've solved for a diameter and I've got an exact diameter, when I go to buy it at the store or at the manufacturing supply, they're not going to offer a 0.131 inch wire diameter. Instead, they're only going to be able to offer me the 0.125. So I'm going to have to make some corrections anyway. Starting with 0.125, plugging in for what my coil diameter should be. Number of active coils will be 11.831. Now remember, if you remember, I told you that we're not going to be able to do this either. The manufacturer is going to be forced to truncate down to the nearest quarter of a coil. So the nearest quarter of a coil would be going down to 11.75. This means instead of achieving the 36 pounds per inch that I desired, what I'm actually getting is 36.19. If that wasn't satisfactory, then I really have to go back to the drawing board. I'm going to have to change either this wire diameter, or probably more likely I'll have to change the spring index to a new one so that I can get exactly to 36 pounds per inch. That gives me a total number of coils of 13.75. I'm plugging in. We now have a free length of 3.156 inches, and that gives me inside and outside diameters. Now you might ask yourself, if I change the diameter, isn't that changing the factor of safety? And the answer is yes, it actually is. Looking at my factor of safety equation and how it was rearranged, it was definitely, the maximum shear stress was a function of D. So this is going to cause a problem. I'm going to have to check and make sure the factor of safety is still okay. As far as problems within that we're going to work with in class, this flow chart that I showed earlier in the lecture is a good way to start. Take our guess, find out what the factor of safety could be. And then concurrently, you can even do it at the same time. Go ahead and find out what your desired and actual spring constant should be, and then there's going to be an iteration that occurs here until we get to where we need to be.